Good evening, everybody. A very warm welcome. My name's Anna Meredith. I have the great privilege of being the PVC Executive Dean for the Faculty of Natural Sciences. And it's a great pleasure to introduce our speaker tonight for his inaugural lecture, Professor James Bell. James is a quantitative ecologist and entomologist with expertise in insect conservation and insect vectors that transmit plant diseases. James was lucky to secure a field technician post at the University of Oxford. These are James's words, so he was lucky. I'm sure they were lucky, very, very lucky to have him. But he first secured a field technician post at the University of Oxford with his partner and now wife, Alison, who joins us tonight, in between his first and second degree at MMU. His PhD focused on restoring limestone quarries back to semi-natural grassland in order to achieve rapid biodiversity gain, and he found that rapid turned out to be quite hard to deliver, but he says he learnt a lot about how systems worked. After his PhD in 1999, he secured postdocs in entomology at the University of Roehampton, University of Warwick, and then at Cardiff, before settling down to a career at Rothamsted Research in 2008. He then secured what he calls his dream job as head of Rothamsted Insect Survey in 2015, which he held for 8 years before moving here to Kiel, and we're very glad he did. James was appointed here as Professor of Entomology in January 2024. I'm very pleased to say and make a very warm welcome to his family who join us this evening, Alison, his wife, and fellow insect enthusiast, who was also formerly head of the bee group at Rothamsted. James and Alison's eldest daughter, Caitlin, who's a private chef, having worked at high-end restaurants in Sussex. Son Harry, who's an electronic engineer, shortly to start a career at Rolls-Royce, and Julia, who is approaching her third year in nutrition at Leeds Beckett. You're all very, very welcome, and thank you for joining us to support James tonight. So welcome also to those of you online, and without further ado, I think we'll start the lecture. James, from the title, he's going to take us on a very exciting journey tonight. Where have all the insects gone? A foray through Britain's habitats and lower atmosphere to find out. So we're all looking forward to that, James. Welcome, and thank you very much.
Thanks for the round of applause. I'm super excited to give this lecture. It's all about insects, of course, and it's a story of migration. I'm going to keep this really at a level that I hope you will understand, but I'm also going to do some technical stuff. But by the end of the lecture, you'll know how insects fly, you'll know how high in the atmosphere they go, and you'll know what the trends are in those insects. So let's begin by introducing my friends, and these are some of the familiar insects that you'll know. All of you will recognize a wasp, a bee, or a dragonfly. But there's less familiar insects there. We only have to look at the fairy fly in the top middle there and how different it is to all other insects. You can see there it's essentially got paddles and feathers around its wing. And it does this because it's so small. Some of these insects with these types of wings are no bigger than a protozoa. And yet, remarkably, they make it up to several hundred meters, if not thousands of meters, up into the atmosphere, which is an incredible feat, given they experience the atmosphere as a viscous fluid, like a thick oil. So they've adapted to move, and they can go high, and they can go long. One of the most famous of all migrations is the monarch butterfly that moves up from Mexico all the way to Canada. And it does this in a multi-generational movement. And we have our own monarch butterfly, if you like, the painted lady. And the painted lady moves up through the sub-Sahara as a multi-generational shift all the way to the UK. And my wife and I were delighted to see it at the weekend, having moved up, as I said, a huge distance from another continent. And so The migration I'm going to talk about this evening isn't a migration of that type. It's a different kind of migration, a daily migration up into the atmosphere and back down again. And I think with the instruments that I'll show you that I used over the time period of study from the last 10 years or so, you'll be amazed that this even happens. So the journey I'm going to take you on is right up to about 4 miles high, remarkably where we can find insects and spiders in an atmosphere that's so cold that other things would freeze. And yet they've adapted their hemolymph, or their blood, so that they are resilient against those temperatures with antifreeze effectively in their blood to stop them from dying. But we're going to take this journey up into the atmosphere, and then we're going to come back down again. And of course, this is all attributed to the sun, which heats the atmosphere and the soil, and it generates this convection, if you like. You can see that, if I've got a pointer here, we can see that with these thermals here, very strong thermals near the ground level. These dissipate and weaken, and at very high altitudes, they're barely non-existent. And this causes the insects with very weak flight to come back down to Earth. So let's begin on that journey and start off with one of the most fascinating events in insects, is the takeoff. That ability to fly, that ability to move by flapping their wings. And I'm going to show you how they take off and what's happening there. So this is a hoverfly. It looks like it has a really strong and fast wing beat, but actually it's about 130 to 150 beats per second, which sounds like an awful lot, but it just isn't. Some of those small biting flies, the no-see-ums, as some people call them, that land on you, they beat their wings remarkably at over 1,000 beats per second. Just think about that for a moment, how much energy is going into that. And so there's various adaptations that insects use, but I want to talk specifically now about a beautiful insect. Others say less so, those gardeners who want to save their roses. But here we're looking at an aphid. And I chose this as my study organism because one of the aphids that I look at, the peach potato aphid, vectors over 200 viruses, is a global pest everywhere you go, apart from Antarctica, for the obvious reason. So understanding that movement, quantifying that movement, can help us understand how viruses are spread, and therefore feeding back into food security, which is one of my other topics that I'm working on here at Keele. Now, I do this with the coolest piece of kit. I dug deep in my pocket, but I couldn't find £140,000. But luckily enough, I got a funder, BBSRC, to support me with this. This remarkable instrument is used by the Natural History Unit with the help of David Attenborough's narration to explore the natural world. This machine has a frame rate of 400,000 frames per second. So you can pretty much take on anything and slow it right down. And what we're about to see now is a short video of the takeoff of the aphid. What I want you to look at first of all is the boundary layer and its position. So around the leaf, there is an area of still air, which is difficult for some insects to actually take off from. So it raises its legs, and then we'll see the flapping of the wings. So in less than 1/10 of a second, we'll see it take off. It seems unstable, but it's actually quite beautiful, I think. So let's explore what's happening in that image and what's actually causing it to become airborne. So we're looking at here are 4 frames at key moments in one wing-beak cycle. That wing-beak cycle starts with a near clap and fling. So the wings are raised high, they don't quite touch, and then they move downwards to the bottom, so a large amplitude, and there's a wing rotation that moves it back up again to start the wing beat again. So imagine doing 120 of those as an aphid every second. So the flight is energetically costly, but it's saved by a unique mechanism that they use. So at position A, we're ready to take off. We're going to go with a downbeat. And what's happening here is that there's a mechanism called the leading edge vortex. And this is a high-speed, tiny tornado that as the wings go down, the tornado passes over the edge of the wing and is then shed as it moves behind it. But this generates a pressure difference between the upper wing and the lower wing. So underneath the wing, there's higher pressure. Above the wing, there's lower pressure. And this is the mechanism that generates lift. You may have heard that the old saying that physicists can't explain why bees fly. It's because they modeled the bee on what an aeroplane does as a fixed wing. But here, when you build in the leading edge vortex, you get lift. And with the upstroke, you get thrust. So lift and thrust, and they move and rise into the air. So let's look at a longer flight showing how the lift and the thrust generate enough energy for it to move forward and upwards. So again, we've got another aphid. This is just 66 milliseconds. So you can already see in a short space of time, it's going to move some distance. Not even a second goes by without it actually rising into the air. So what you're seeing here is the takeoff, and you can see an angle of flight, one that's rising, and that's due to that combination of leading edge vortex and the lift that is associated with it with the thrust. Now, it's a weak flyer, and I have to say that when it takes off, it's in control of its flight. As soon as it raises up into the upper atmosphere, then it's at the mercy of the winds, and I'll explain that a little bit later. But there were some new discoveries that I made, and this is one of the weirdest insects, really. One of the standard motions for strong-flying insects is forward flight, so where they can literally go horizontal and parallel with the ground. And that's unusual because it suggests real control in terms of their flight. But also, aphids feed on the underside of plants, and if you do grow any vegetables or roses, you'll find them on the underside. So naturally, an adaptation here by the aphid is that it can fly upside down, of course, because it's got to launch into the atmosphere from underside of the leaf. So it drops down and happy to go for quite a distance upside down with no difficulty at all, which I think is incredible. We've got other insects, if you like, arachnids even, so the spiders and the pseudoscorpions that also take flight. But remarkably, these do not have wings. They have different behavioral adaptations. What we can see here are 4 different types of winged insects, flies and parasitoids. But attached to their legs are pseudoscorpions. We have nearly 30 in the UK, and these pseudoscorpions are attaching themselves to the legs. Some of them are so adapted to their host that they can detect the chemical signals that they're present, group around a hole or a structure where they live, attach themselves, and then take to the air. And because often these niches are really small, they know they're going to land in a habitat they like. So in the studies that I've done on pseudoscorpions, on compost-associated pseudoscorpions, they use this foray, this attachment, this hitchhiking to move around, would generally land back into another compost heap. So it's less risky than you think it is, but still, it's going to go some way, and it doesn't know for how long or how far. I did my PhD on spiders, and to me, spiders are honorary insects. They may have 8 legs, but let's just ignore that, because here what we're looking at is one of the, I think it's one of the greatest things I think I've taken a picture of. What we're seeing here is a ballooning spider. A ballooning spider, a money spider that you're all familiar with, that will land on you. They can't bite you, and even if they had venom, they can't penetrate your skin. They're perfectly safe to hold. What we're looking at here with the arrow is the drag line. So at about a meter a second, it can pay out this silk. This silk then is the way they take off. So you think of an opposing force from the corner of the screen here that is forcing the drag. The drag is forcing an energy in this direction. You can see that the spider attached to the grass head is holding on, and when that drag force is sufficient, it will then let go and take to the upper atmosphere. Now, of course, this isn't such a controlled mechanism as flight, but it's very effective. We have speculated for a very long time how they know that the conditions are conducive for movement. And here what we can see is a Trichobothria. The Trichobothria is a pit here with a hair, and it's innervated, or it's got nerves at the bottom in the base in this capsule here, which it used generally to detect insects, their prey. So it's in the four cardinal directions: north, east, south, west. So, for example, when the hair is displaced by a very weak wind caused by the prey displacing the air at about 1 millimeter per second, which is tiny, it can detect it. The nerve switches on inside and says, move around to the left or to the right and attack. It has several sensors on its body, and this is just one. We speculated this may help spiders detect the wind conditions for movement, but actually it's possibly to do with the energy or the electricity in the atmosphere that this can also detect. So high electricity is conducive. So we experimented, and it was in the days when you could pretty much do anything and find people with the expertise to do it. But this is the Rothamsted full-speed chamber. So it's a 9-meter chamber where, when I started to use it, I found loads of hypodermic needles at the top and thought we had a drug addict, but it turns out we had a spore addict, and the guy who was doing all these experiments was dropping tiny droplets with fungal spores in it, trying to work out what the splash zone was at 9 meters. Having cleared that all up, we made a full-speed chamber, and at the top we had a gate 1, where the spider was being dropped, and at the bottom we had gate 2, where the timing and the recording of those spiders dropping stopped. So here's the top of the full-speed chamber, and what we're trying to do is understand how important the silk line length is and the mass in terms of movement. What we're expecting to find is that when you increase the silk line, the drag helps the spider to slow its fall speed, which is what we detected here. We placed the spider on a hot wire. We allowed it to naturally fall, and when it went past the gate, it triggered the hot wire to turn on. It burnt through the silk, and away it went through the full-speed chamber. And we took that to understand its capacity to control the flight, and we conjectured that actually, with longer drag lines, spiders could actually control the distance they went. Surely that's true, because we've just demonstrated in this model. However, I met a theoretical physicist, and things began to change, and he stroked his beard for a very long time, and I asked him, look, I think spiders can control the distance they go. And I said, well, if they can increase their drag line, then they can say, okay, I'm going to release a drag line for 1 meter, and therefore I'm going to go X far. That's true, isn't it, Andy? And Andy decided to model it, and he's so clever that he built an atmosphere that resembled the atmosphere that the spiders might move in. And what we overlooked was that you might as well have a very long drag line, but actually the drag line is never going to be taut. It's only taut when it's taking off. And after that, it curls. And here's a picture I took on an SEM, and it bends. And as it curls and it bends, the forces aren't equal, and such that the drag line can't be predicted in terms of the forces and therefore how far it could go. So we dismissed that idea, but got a couple of nice papers out of it. So that's always good. Just to demonstrate what's around you so you understand and can predict what's happening in terms of insect movement. If you see this kind of day in the early morning where you've got mist and very cool weather and still air, this is not an opportunity to actually go far or go up at all. We call this neutrally stable. So it's actually just very still conditions. And when you're a weak flyer, you don't need that. What you need is non-ideally convective. So this says basically it's not too strong in terms of the thermals that are coming up from the soil, and it's not too windy, such that if it were high winds, they would be pushed back down to the ground, but instead they are non-ideally convective. And so with that, both the spiders, the pseudoscorpions, and those winged insects have taken off. And now we're going to go up, and we're going to go to the mid and high altitude zones. The kind of kit you need to explore that can be really basic, and we'll see that with David Attenborough. But also, if you want to really measure things, individual insects up to 1,600 meters, you need a vertical-looking radar that Rothamsted had, and I modeled 1.7 million flies, beetles, and true bugs in what we call a daytime convective atmosphere, where insects in the early morning move up, and they come back down again. And this remarkable piece of kit can tell us about individual insect mass, its speed, its shape, its cardinal direction relative to the winds. Everything you want to know about its performance can be gathered by this radar beam that hits the insects and sends the information back down to the dish. So taking that 10-year time series, I just have one image in one day. And what I'm going to show here is a time period from the early morning, so it's the 6 in the morning, all the way to early evening, 6 in the evening. And what I'm showing here is the altitude that we're looking at using the radar, up to nearly a mile high. And the contrast between these two is simply that one is a warm day, the one above, and one is a cool day, the one below. And the colours indicate the densities of those insects. So a red colour here has high density of insects, and a blue at the top, very low density. And it's very quick to see how that a warm day generally gets many more insects being active in the atmosphere. Typically, the largest number of insects take off at 8 in the morning. Some of them may move down again, so they're taking short distance flights. But it's a question of whether they choose to or they're forced to move into the upper atmosphere, and they do. And the remarkable thing is that they do this within a day. And they may move hundreds of miles by doing so, depending on the wind speeds in the upper atmosphere. So the contrast between the cool day and the warm day is stark. A cool day doesn't generate those thermals that they need. These weak-flying insects need that heat from the soil to generate that convection or those thermals to move them up. They need assistance. And so when you remove the effect of the sun, what you see is only the strongest insects getting up high. Of course, David Attenborough was 100 last week, and here what we see him doing is looking at insects at 4 miles high. He went up a hot air balloon, he put a mask on, he wrapped himself up, he could barely speak whilst giving the narration. And I think it's actually incredible that we see these things, but that's not the highest insects can go. We can go up to 6 miles high and still find them. So they are probably stuck. The forces are so strong that they can't oppose them. And they may die up there. It's unlikely they can come down unless they're the strongest insects, and they choose not to go up this high. So I think it's very unlikely. So the biggest study was just published recently where we used weather radar, and weather radar are quite different to vertical-looking radar. Vertical-looking radar targets individual insects. Here we're looking at weather radar that actually looks at volumes of air. In this case, 1 kilometre volumes of air. And the biggest number I've ever published is a quintillion insects, a billion insects, or 2 billion insects were studied over 8 years. And we targeted the mid-zone, that one you saw on the slide earlier, at 7 to 500 meters. That's where most of the insects, the highest densities, can often be found. And we looked over Great Britain, 35,000 kilometers. So what's happening here is that instead of the beam from the vertical-looking radar, we've got a scanning radar that actually sees the insects. And it's really the difference between raindrops, it's tasked to capture, and anything else. And then with the anything else, that includes spiders, insects, and other biological material, which we use the reactivity to split. So with that, we found some fairly cool stuff. We were able to work at scale, and across the UK, widespread decline in abundance of nighttime insects, but not of daytime insects. We saw pronounced losses in the north relative to the south, caused by differences in warming, and this may be due to different climate effects in southern Britain compared to, say, northern Britain around York and further. And what we saw was something unusual we couldn't quite explain, but thought about it for a while, that strong positive effect of urban cover due to warmer cities. So we have these heat islands, these cities that are warmer. So relatively speaking, in cooler days, they may be beneficial. And they may be collecting there because of light pollution. So light pollution across the globe is increasing at 10% per annum. So the higher numbers is probably a bad thing rather than a good thing, because they're reconcentrating the numbers to be over cities. So profound things are happening in our atmosphere, and we don't really know it's happening. So let's just have a look at what happens when insects start to descend. They'll probably descend in the same manner as they went up. Andy, who you saw, worked on another paper to show that the winged insects, the spiders, can add some energy to the direction of wind. So if it's going up, they can add their own energy to go up, but they can't oppose it. So when the air is going up, they can't come back down. But very strong insects like dragonflies and some damselflies can reach heights of 500 meters, and they can purposely make a difference to the movement and oppose that and come back down should they wish. So these small insects that I study, that they can't. They are at the mercy of the wind. So here we are coming back down to Earth. We're just above the flight boundary layer. The flight boundary layer is an area just close to the ground that's probably 10 meters in height. It's the area where most insects can be found, and most insects don't leave it. They stay there. So they stay there because their food and their habitat is there, and they can find their mates quite easily without going long distance. That said, a small proportion of any species might try to go high and long. These remarkable things are the suction trap at Rothamsted Insect Survey. We have a network, or had a network, over the whole of the UK where we would collect the catch, and we were tasked with telling farmers about the virus vectors, those aphids that I talked about. And those obviously are really serious, so we would forecast those for farmers using the data from the suction trap. But brilliantly, the insect survey kept all the non-aphid sample, and there were thousands of species in there. And so they would be committed to an archive. And so with the next study, I'm going to look at what that data say about insects. So here's the archive. We can find some very familiar insects, the ladybirds, the lacewings, and the hoverflies, the larvae of which eat aphids. So these are the good guys on the left-hand side. And onto the right-hand side, we've got the weird ones. So we've talked about pseudoscorpions and the foray, and there are plenty of those. But also there are these feather-winged beetles. Now, these are absolutely tiny. They're measured in microns, which is nothing. And they have this adaptation of using these feather wings, and you can see the position of them. Those tiny beetles are rowing in the air. They've left behind flying. The air is so viscous, they are moving as if you were on a boat rowing across water. That is their adaptation. And if you look up feather-winged beetles, you can find some cool stuff on YouTube from a Russian group who does all this research. One of the things that we have done over the last 50 years is apply vast amounts of insecticide to our crops. And some have been absolutely terrible and noticeable, and their effect on wildlife has been devastating. I'm thinking here of DDT and Rachel Carson's Silent Spring, where it caused, these chemicals caused eggshell thinning and the collapse of those populations. And over time, we've got slightly safer, but yet still what I find remarkable about this graph, which is a trend over time telling you whether they're declining or they're rising, is that whatever we seem to throw at them, whatever new technology, they persist. And they're almost flatlining here with lumps and bumps. So this black line is a trend line. It goes up and down, but generally, on average, you could draw a line across here and say, do you know what? Not much has changed, and that's true. And it's based on vast amounts of data. So this simple line is underpinned with 16 million individual aphids. It's brilliant to have that long-term data, then link with other organisations that also have long-term data. So the BTO, the British Trust for Ornithology, have equivalent data starting again in the 1960s as the Insect Survey does. And we were able to match swifts, swallows, and more recently, bats with the Bat Conservation Trust to look at the relationship between the predators, these birds, and the prey, the aphids and the other insects. And the swallows, which are probably the best relationship between insects and birds, shows that with our data and with the BTO data, looking at breeding success of those swallows, there's a positive relationship between swallow chick survival and the biomass of those aerial insects. And the survival through to fledgling is higher where insects are more abundant. Basically, what we're saying is birds need something to eat, and insects are really important. Where they are large in number, they do better. But of course, some insects are declining, and one of the most highlighted groups are the moths, the nighttime insects. Obviously, their link with light pollution is very strong. And sadly, looking at over a long period of time from the 1970s to nearly the present day, 7.5 million insects tell us that they're not doing very well, declining by a third. And if you look at the lumps and bumps of this otherwise straight line, you can see that they try to change the course, but then they go back down again. So it's a very lumpy, bumpy crash to the bottom. I want to talk a little bit about machine learning. And machine learning can be understood very simply, in so much as it's an algorithm that uses one data set to train itself to understand the relationships between different types of data. Here we're talking about environmental data and insect morphologies and traits, a complex set of data, and the predictions we can make from that. So we decided to take a big chunk of UK data. It's based on citizen science data. Now, if you are a person who goes out in the field and uses an app to record the insects you see, we've probably used your data because we studied 1,252 species across the UK over 30 years. We did see that between the regions, between Wales, between the Midlands, between north and south of England, trends that were different. But actually, we also saw that over the UK, no decline since 1990, but instead we see these unusual patterns locally. So there is some good news, but the difference here compared to all the other stuff that I've talked about is we're looking at occupancy data. That is, if you record an insect in a space, you're recording an individual of one, and then you're walking off. And so it's a different type of data. It gives a different type of picture on insect declines, but it's still very useful to understand. So I know this looks confusing. It's meant to. It tells the story of how a machine learning model works. But essentially, and you don't have to understand this, what you want to know is where it is. So you have this training data set. So you take half the data you have, and then you take all the environmental information that you can, all the species types of traits, such as body length, and you work on solving this problem with these data sets, building in what you know about the current observations to make predictions about where they could be. So these are people walking around the UK recording insects with the app, and they can go only so far, and certainly the northern part of Scotland has fewer records for obvious reasons. So we can then predict where, based on the environment and their traits, where they could be. So I hope that is understandable. Let's suffice to say, it runs for days with all those species, takes a very long period of time. But what we found actually is this change in the environment where in increasing urbanization, we get this fragmentation, so tiny slivers of habitat broken by very large roads or very large housing estates. And this changes their course to a declining population where this may occur, but also a simplification of the habitat. So agriculture that provides our food needs also tells us that actually it's having a damaging effect because it's actually taking away the diversity of those landscapes and simplifying it, where they're removing host plants and prey, for example, for those insects. So those are the two main drivers we identified. We have a new paper out at a journal, and we're calling it Cinderella Biodiversity. You may know the story of Cinderella, who wasn't allowed to go to the ball, even though she had all the qualities to do so. But she found a way. And so equally, all these very small insects are ecosystem engineers. They're doing great work, but yet no one notices. They're not charismatic, they're not necessarily colourful, they're just really small. And so we took a big sliver of that data, and we had people working full-time to identify all those insects. For any entomologist, 600,000 insects is a large number. And we took 70 groups. Many of these groups have never been studied before, and it's unfortunate that actually they're all in Latin, but actually I think what you can see here is the vastness of the data. This looks really intimidating, but it isn't. Let me explain. So we have 4 sites, Newcastle, Hereford, Rothamsted and Starcross, places that are quite far apart in the UK. And that applies to this section here, so the sites are the same. And what we can see here is this side of the graph is the measures of abundance, so how many there are at the site. And this is when the season starts. So a blue for the season start means they're flying earlier, they're occurring earlier, a measure, a proxy for climate change. And here what we're seeing is a change in abundance. So red, there's more of them. Blue, there's less of them. And without explaining any more, you can quickly see with a vast amount of data what's happening. Insects generally across those 70 families are increasing in number. Insects across those 70 families are occurring earlier, probably due to climate change. I want to highlight one fantastic group. These are the rose beetles. They're my favorite insect. And these beetles, in this, what we call a genera, so very, very close related insects, number more than 3,000 over the whole globe. And that's equivalent to some of the larger vertebrate groups. So these insects are really important. We've told people what's happening, and here we see, if I can find it, which is around here, the staphylinids. I can't quite see it at an angle. Here they are, look. That actually, for the first time, we have trends for 4 sites. We can say something about them. We've started the process, and that's a fantastic feeling to have done. So I want to conclude with my last slide, some basic understanding. I hope you've enjoyed the journey we've been on up and down the atmosphere. And I've focused on the less well-known, small and otherwise tiny animals. I haven't spent time looking at butterflies and moths because that work has been done. We need to have this information to affect change. I've called these Cinderella species because we know very little, yet they are ecosystem engineers and they are qualified to actually be highlighted. We have seen how insects and others can take different strategies to become airborne. Insects have wings, more often than not. Spiders have a mechanism called ballooning, and pseudoscorpions can hitchhike. They do this differently, and they modify their behavior. Most of those small insects cannot come back down to Earth without the assistance of the atmosphere. They're probably doing this for food or to escape rapid landscape and climate change. We know how rapid that is. Yet we have no idea what is the primary cause, and that will be interesting to understand because it's certainly an interesting policy point. So the evidence suggests that these Cinderella species are not doing so badly compared to other groups, the larger insects like moths that are declining by a third. But they are occurring earlier, and there may come a day very soon when we lose winters and we have a continuous subtropical atmosphere where insects and others thrive. For example, swallows, a proportion of which now do not migrate over to Africa. They stay in the UK. And we're seeing that with insects too. I haven't mentioned my collaborators. There are many. I have purposely not mentioned any of my papers. There's quite a few. And if you'd like to look at those, you're welcome, but you don't need to. And so hopefully I've told you enough to understand what's happening on a daily basis with insects in the UK. And thank you very much.